Chapter 17, Integrated Aircraft Systems, Case Studies. Starting with the introduction, modern aircraft are highly integrated systems in which avionics, propulsion, electrical, hydraulic, pneumatic, environmental, and flight control subsystems operate as a coordinated whole. Understanding these interconnections is critical for pilots, for engineers, and maintenance personnel, as failures rarely remain isolated. One failure would lead to another. Okay, not one failure can bring down an airplane. It would be a sequence of events. This module synthesizes acknowledge or the knowledge from previous chapters and applies it to operational scenarios and real world case studies. Briefly, not too much extensive. 11.2 System Interconnections and Dependencies. Aircraft systems are designed with multiple layers of dependency to optimize efficiency, weight, and safety. Electrical, hydraulic, and avionic integration. Many primary systems rely on electrical power generation and distribution. Engine-driven generators supply AC power. Transformer rectifier units, TRUs, convert AC to DC and rectify the voltage level, meaning that if you have a low voltage, it would bring it back to the correct level, or if it was a high voltage, it would pull it down to stabilize the voltage being produced. Okay, just like the power supply, by the way. The rectifier in the power supply in the UPS system works the same way. DC buses power avionics, sensors, and control computers. Okay, so these three are powered by or fed by the DC buses. Electrical pumps provide backup hydraulic pressure. The electrical power balance may be expressed as P gen, or the power that is produced by the generator, is equal to the power consumption of avionics, power of the hydraulic system, power of environmental system, which is the air conditioning, plus the lost power, which is the transmission losses, okay, or the power losses within the transmission lines, okay, the power lines, the electrical wiring, resistance, and other stuff that waste power due to heating effects, okay. We're not talking about dangerous heating, but every wire that has a current passing through it would generate heat. So not all the power would be effectively used by the different systems of the aircraft. Some part is wasted. 11.2.2 Pneumatic and environmental dependencies. Bleed air extracted from engines supplies cabin pressurization, wing and engine anti-icing system, air-driven hydraulic pumps. Okay, bleed air mass flow is given by M is equal to rho AV, where rho is the density and A is the cross-sectional area. V is the velocity of the airflow. So rho is the air density, A is the duct cross-sectional area, and V is the airflow velocity. Again, so the bleed air extracted from the engines would supply the cabin pressurization, making sure that the pressure in the cabin is comfortable for passengers. The wing and engine de-icing systems, like the de-ice boot at the wing leading edge and engine heating. Air-driven hydraulic pumps. Okay, so these three are the main systems powered, okay, or that consist the pneumatic system, and they are powered by the, or like fed by the pneumatic system. Flight control and sensor integration. Fly-by-wire systems integrate air data computers, or ADC, inertial reference system, IRS, which is called, by the way, in Boeing 777, I think, ADRU, air data inertial reference unit. Flight control computers, or FCC. Control law inputs may be simplified as delta is equal to a function of alpha q Vn, where delta is the control surface deflection, alpha is the angle of attack, q is the pitch rate, V is the airspeed, and N is the load factor. Okay? So the deflection of the control surface is a function of the angle of attack of the air, which resists that deflection. Q, which would be the pitch rate. V is the airspeed of the flow, the airflow, and N is the load factor. Normal, abnormal, and emergency scenarios. Normal operations. Under normal conditions, systems operate within design envelopes with full redundancy available. Monitoring systems continuously verify that system pressures and temperatures are nominal, electrical bus integrity is correct, and data consistency between redundant sensors, meaning they are pulling the same correct values. Okay, that is data consistency. Abnormal scenarios. Abnormal operations involve partial system degradation without immediate safety threats, such as single generator failure, hydraulic leak in one system, and sensor disagreement warnings when two sensors are collecting conflicting values. Reliability of redundant systems is expressed as R total is equal to 1 minus pi, which is the sum of 1 minus Ri, the different reliability factors, okay? From 1 to n, depending on the number of the independent channels. Emergency scenarios. Emergency conditions require immediate crew action such as dual engine flameout, smoke or fire warnings, rapid decompression. Okay? Time critical response may be modeled as T response should be less than the critical time, which is the time before loss of controllability or survivability. 11.4 Real world accident and incident analysis. Okay, now this would hopefully be more expounded like in a different session. So let's start here with some scenarios. System interaction failures. Many accidents result from cascading failures rather than a single fault. Exactly what we mentioned before. Typical contributing factors include sensor failures leading to incorrect automation behavior. So the autopilot would be relying on false data in order to control the aircraft. Misinterpretation of warnings, that would be a human factor error, and loss of situational awareness where the aircraft loses vital instruments and no longer can tell whether he is going up or down, pitching, whether he's in a roll, in a dive, in a climb, all of these things, especially during night flights. Okay, example, analytical chain, you would have sensor fault leading to incorrect data, leading to automation response that is incorrect. Why? Because it's based on false premises and false data collection, which would also get us to a crew confusion. Okay, that would be the final result, which can be fatal, by the way. Human-machine interface considerations. Alert overload probability increases with system complexity. So the probability for error is directly proportional to the number of alerts multiplied by the cognitive workload factor. So as the number of alerts increase within the cockpit, this becomes more taxing to the pilots in order to deal with it. Okay, so the crew would become confused. Plus, you add to that the cognitive workload factor, how much cognitive ability the crew has in order to deal with the number of alerts that are being displayed. So when you have a high workload, okay, that would decrease the ability to factor in the different alerts and to deal with them, which would increase the human error, okay, that can happen during the processing and the troubleshooting of the fault. 11.5 System failures and troubleshooting approach. Fault isolation philosophy. Aircraft systems use structured fault isolation, which means that the pilot should identify the affected system, verify indications, and cross-check sensors, because you would have different readings at times from different sensors. So he needs to verify that the fault is actually occurring. 3. Apply checklists and procedures in order to troubleshoot the problem. And 4. Isolate the failed component. Logical troubleshooting model. Troubleshooting follows Boolean logic. So, F, which is the system failure, is equal to A, standing for power availability, and B or C. B stands for sensor integrity, which means the sensor is together and working properly, and C stands for or represents the control logic health. So, in other words, for a system failure to check out correctly, to pass, in other words, also, for a system failure to be validated as failure, as an existing fault, it should meet the following conditions. A, at first, meaning the power should be available, A should be true, and at the same time, one of these two arguments would be true. So, either the sensor integrity is standing also, which means that the sensor is reliable for the measurement, or C, which is the control logic health, would be true. So either one of them is true or both of them is true, and the power is available at the sensor. This would check out correctly with a correct system failure being reported to the cockpit or the notification instrument, the notification display. Let's talk about BITE, or the built-in test equipment. So what is it about? Modern aircraft employ BITE systems to record fault codes or register fault codes for later assessment or online, like real-time assessment and troubleshooting, perform post or power on self-test. By the way, this is the very same procedure that your own computer performs the moment it starts up. So when you start up your computer, before loading the operating system, what happens is that the firmware, which is stored within the ROM, the read-only memory, it is loaded at first, and it runs and it goes to check the different faculties or different boards of the system, such as the RAM, random access memory, which is the dynamic memory of the computer, the hard drive, different chips, different USB buses, your hard drive itself, your CD-ROM, if you have one, if you still have one. So the same operation, and by the way, this is the operation that runs, and once everything has been checked correctly, this is when the operating system would be loaded and your Windows would start on your own computer. So the same process goes for aircrafts. The airplanes do the same thing. You have a post test, and when the post checks out correctly, so when it passes, the aircraft passes the test, especially in the Boeing 777 Boeing, it will beep twice, signaling that the system had worked correctly. It had passed all the tests and everything is proper and in order. Okay, so the same thing goes for your own aircraft. And this is when you would see the displays such as the PFD, MFD, all different displays would run. They would open up. Okay, now, third, to assist in maintenance diagnostics. So the BITE system is necessary to assist in diagnostics, to understand what kind of faults have occurred or occurring during the flight or during ground operations, okay, during ground maintenance. Summary: integrated aircraft systems demand a holistic understanding of interdependencies, failure propagation, and human factors. Effective monitoring, well-designed alerting systems, and disciplined troubleshooting procedures are essential to maintain safety in increasingly automated aircraft environments, because aircrafts are becoming more relying on computer systems than manual pilotage, so to speak.